A coffee cup calorimeter with two materials. There are two types of coffee cup calorimeter type problems. There are problems that involve two materials and problems that involve a reaction and a solution. So this is definitely the kind that involves two materials. It says that a 22.23 gram gold ring, so the gold ring is one of the materials, initially at 93.7 degrees Celsius, is submerged into 55.1 grams of water at 27.4 degrees Celsius in a coffee cup calorimeter. What is the final temperature of both substances at thermal equilibrium when all temperature changes are complete and the final temperature of the pure gold and water are equal? Thermal equilibrium, or equilibrate the temperature as we call it in lab this past week, talks about temperatures stop changing. And in this case, the temperature of the gold and the water will stop changing because they will be the same. And the experiment, very simple. Take a coffee cup or two sometimes with some water in it, and that water is at 27.4 degrees Celsius, and place a gold ring into it, and the gold ring is 93.7 degrees Celsius. So place it in. There will be heat exchange between the gold ring and the water, and that will bring the two temperatures to the same level. Now our equation for this starts like this. Q of the first material, which we'll call Q sub gold, equals minus Q of the water, where Q is our symbol, lowercase q is our symbol for heat, and that the minus sign just means that while one thing is giving off heat, energy, and that's going to be the gold ring since it's warmer, the water will be taking in the energy, the heat energy, and the minus sign just notes that there's a difference in the direction of these two processes, which is an important concept, especially for engineers, because the direction of heat flow matters for sure. Okay. Then for each material, the equation goes like this. So Q of gold is going to equal the mass of gold, which is M sub gold, times the specific heat of gold, which is C sub S gold, times delta T gold. And this is the expression for Q, the heat energy for the gold. If we change all the subscripts for water to water, it's the same type expression for water as well. So what I'm going to do is I'm now going to write out the entire expression down here. Then we'll fill in all the numbers that we have, and we'll see that there's only one thing that we don't know. That's going to be the final temperature. Before I do that, I'm going to turn this delta T gold into, because delta T means change in temperature, and I'm going to change it to T final of gold minus T initial gold. Everything in science, and specifically chemistry in this case, is always final temperature minus initial temperature. Let me go ahead and fill all these in. So it's going to be for Q gold, it's going to be this expression right here, mass of gold, times specific heat of gold, times, and now I'll put in T final gold minus T initial. T initial gold. And I think I might put the other side down here a little bit because I wrote a little big. Now it says is going to be equal to the negative of the mass of water times the specific heat capacity of water times T final water minus T initial water. And I'm just going to use a W now. Well, no, I should use water. Minus T initial water. There we go. So that's what our expression looks like. Now let's go ahead and plug numbers in. The mass of our gold is 22.23 grams. Our specific heat of gold, AU, is given in the problem statement, 0.129. joules per gram degree Celsius. Our final temperature of our gold and our final temperature of our water will be the same. That's what it means by thermal equilibrium. So I'm just going to write T final minus, and our initial temperature of our gold is 93.7 degrees Celsius. Plugging in for the water, we have 55.1 grams of water. The specific heat capacity of our water is on our conversion and equation sheet. There it is. For liquid water, liquid H2O, which is water, it's 4.184 joules per gram degree Celsius. And I'm going to stack up my units there to save space. And then I've got T final minus T initial, which is 27.4 degrees Celsius. And it sort of fits there. Now, the only thing there is to do is to, oh, and I almost forgot my minus sign. Got to include the minus sign there, or things get crazy. So now the only thing to do is to solve this. The way that I like to solve this is I like to multiply all my terms out, so I get 22.23. It's what I like to say, we're off to the algebra races here. 22.23 times 0.129 equals 2.87. That's going to be these two, and it's going to be that times TF, so 2.87 TF minus that same number times 93.7 equals 268.7. There we go. Sorry about that. And I'll just go 269. And I'm going to leave out my units here. We can talk about units in a minute if you'd like. Now it's going to be these two numbers, the 55.1 times the 4.184 times T sub F. So there we go. 230 or 231 TF. And so let's see, minus that first term, minus means the second term is going to be a plus. Oop. And that second term is going to be 55.1 times 4.184 times 27.4. And I get plus 63.17. Any questions so far? If not, then the only thing to do is to collect like terms. I've got a 231 TF and another TF term here. I'm going to bring that over to the left-hand side so that they both are positive. So 2.87 plus 231. I get, well, I'm going to round this to 234 times T sub F. Bring the 269 over to the right-hand side. 269 plus 63.17, 65.86. And then divide through to find T sub F. 65.86 divided by 234. And I get 28.1 degrees Celsius. Always have to check for the problem here because it's easy to mess up the math. Is our final temperature between our two initial temperatures? This must be true. So our two temperatures, so our T initial was 27.4 and 93.7 degrees Celsius. So we are between our two temperatures. Another point I'll make is that the specific heat capacity of the water is over or approximately, let's say, 40 times greater than the specific heat capacity of our gold. That means it takes a lot more energy to heat up our water than it does to cool down our gold. And that is reflected in the fact that the final temperature is much closer to the initial temperature of our gold. So all that hopefully makes sense and suggests that we've done our answer correctly.